In the previous lecture, we have started to discuss the concept of angular momentum and inertia tensor of a rigid body. Okay? And you have seen how we can define the angular momentum, how the concept of inertia, how the concept of inertia tensor develops from the expression for angular momentum of a rigid body. Okay? Now, we are going to see a very important concept, which is just related to this. Actually, in this present lecture, our aim is to discuss the principal moment of inertia, or you can say principal excess and principal moment of inertia. In other words, you can say we are going to see the concept of principal excess transformation. It means if you know the inertia tensor, that is the moment of inertia of a rigid body and product of inertia, how we can transform these values relative to a particular set of axes which is called principal axes. So what are these principal axes, how we can transform the inertia tensor in this principal axis, we will learn in this present lecture. Actually, you have seen in the first lecture on this subject that we have assumed a rigid body, as you can see in this figure, which is rotating about a fixed point O inside the body, and an axis passing through this fixed point, which is called instantaneous axis. The body is rotating about that with angular velocity omega. Okay? And considering this rotation of the body about the instantaneous axis, we have calculated the angular momentum of the body, and from which we have seen the concept of inertia tensor. Now, to know the principal axis transformation, we will need the final result of the previous lecture. So you can see I have mentioned here, you have learnt in previous lecture that the angular momentum vector is represented in matrix notation by this column matrix Lx, Ly and Lz. These are actually the components of angular momentum vector along the body set of coordinate axes. Okay? And that is given by this matrix, which is a 3 by 3 matrix, which is actually inertia tensor, operated on the column matrix omega x, omega y, omega z, which column matrix actually represents the angular velocity vector of the body. Okay? So this was our final result, and we have seen that this 3 by 3 matrix, which I have defined here, was denoted by the symbol I, and this I is called inertia tensor. This is a second order symmetric tensor, because you have seen that actually in this case Ixy is equal to Iyx, Ixz is equal to Izx, and Iyz is equal to Izy. So this is a symmetric tensor. Okay? Actually, the symmetric nature of this I bears an important advantage. And what is that advantage? Actually, the advantage is we can choose a certain system of body axes with respect to which the off-diagonal elements of this inertia tensor should disappear, will be zero. It means this off-diagonal elements, that is Ixy, Ixz, Iyx, Iyz, Izx, Izy. These are actually the off-diagonal elements. Due to the symmetric nature of inertia tensor I, we can choose a certain system of body x's with respect to which all these 6 off-diagonal elements will be equal to 0. Okay? And only the diagonal elements which are I xx, I yy and I zz, these will be non-zero, that will remain in the expression for this inertia tensor I. Okay? In fact, the x's relative to which the off-diagonal elements of this inertia tensor A are 0, such x's are called principal x's. That x's are called principal x's. So you can say that such x's are called the principal x's of the body. Okay? And the corresponding moment of inertia as the principal moment of inertia. It means since only the diagonal elements remain non-zero with respect to such set of coordinate x's, so the diagonal elements represent the principal moment of inertia. Okay? So if I have mentioned all those facts here, you can see I have written here. The symmetric nature of I bears an important advantage. We can choose certain system of body x's with respect to which off-diagonal elements should disappear and only the diagonal elements remain in the expression for I. And such x's are called principal x's of the body, and the corresponding moments of inertia are called principal moment of inertia. I think you have clearly understand. So if you denote the inertia tensor now by the symbol I prime, okay, and you take the principal x's as x dashed, y dashed and z dashed. These are now the principal x's. Then what will happen? As I have told you that all the off-diagonal elements of this matrix for I dashed will be 0. And only the diagonal elements remain non-zero. And we consider that these I1, I2 and I3 are the principal values of moment of inertia with respect to the axis x dashed, y dashed and z dashed. So in this condition, this inertia tensor I dashed will be expressed in the form of this matrix. This matrix is also a 3 by 3 matrix, but you can mark that only the diagonal elements of this matrix are non-zero and all the 6 off-diagonal elements are 0. Okay? So this is the matrix representation of principal inertia tensor. You can say this principal inertia tensor. Okay? Now see, as we have considered that I1, I2 and I3 are the principal values of inertia tensor now with respect to the principal axis. So relative to those axes, we also consider that this omega 1, omega 2 and omega 3 are the components of angular velocity of the body relative to these axes. These principal axes, that is x dashed, y dashed and z dashed. And similarly, we also assume that the components of angular momentum vector L are L1, L2 and L3 with respect to the 3 principal axes. Okay? So in this condition, if you will write the components of angular momentum vector as a column matrix on the basis of this equation A, then what will be that equation? You can see in here I have mentioned that very equation in equation 2A. You can see that this column matrix L1, L2, L3 This column matrix or column vector represents the components of the angular momentum vector. Okay, and this is your inertia tensor, principal inertia tensor, which is a 3 by 3 matrix whose diagonal elements are I1, I2, I3. These are principal values, and all off diagonal elements are 0. And at the place of omega x, omega y, omega z, now I have written omega 1, omega 2, omega 3. This column vector represents the angular velocity vector. So now, what will be L1? If you want to find L1, you can easily find it. You can see that will be I1 times omega 1 plus 0 times omega 2, which is 0, plus 0 times omega 3, which is 0. So L1 is simply equal to I1 omega 1. Similarly, you can see that L2 is simply equal to I2 omega 2, and L3 is simply equal to I3 omega 3. Okay. So mark the difference. In the first lecture on this angular momentum, I have told you that actually, and you can see from this result, that at the place of L1 here there is Lx, and you know what is this Lx? Lx will be Ixx omega x, okay, plus Ixy omega y, plus Ixz omega z. What you are seeing here, the x component of angular momentum vector does not depend only on the x component of angular velocity, but it also depends on omega y and omega z, and we express this Lx as a linear combination of omega x, omega y and omega z. So I have told you in the previous lecture that in general the L vector is not parallel to this omega vector in general, but in a specific condition L will be in the direction of omega. It is possible. What is that specific condition? Now you can see. This is the situation. When you are talking about the principal axis, in that condition you can see L1 is along the direction of omega 1, or you can say L1 depends explicitly on omega 1, only on omega 1. It is completely independent of omega 2 and omega 3. Okay. So I have mentioned it here. You can see that it is clear from this equation 2 that each of the angular momentum component along a principal axis is a function of corresponding angular velocity component only. L1 is a function of only omega 1, L2 is a function of only omega 2, L3 is a function of only omega 3. Okay? And related to it by a principal moment of inertia about that direction. Okay? So in general, if a rigid body is rotating about a principal axis, not any other axis, about a principal axis, in that condition, the angular momentum vector L and the angular velocity vector omega are directed along any one of the principal axes, and so we will write in this condition L equal to I omega. Although I have so from this equation you can say that L is parallel to omega, but you can claim that in my previous lecture I have also written the same equation, L equal to I omega. I have written the same equation, okay? But I have not told in that case that L is parallel to omega. And if you will say that L is parallel to omega, that will be wrong in that condition. But in present situation, we will certainly say that L is parallel to omega. So what is the difference? Why now we can say that angular momentum is along the direction of angular velocity vector omega, but in the previous case L was not in general directed along the direction of omega. What's the difference? Actually, the meaning of I in present case and in previous case is different. Why it is different? What is the difference? Actually, in previous case, this I was a second order tensor. Okay, that was a tensor, not a vector, neither a vector nor a scalar. But in this equation 3, actually, this I is a scalar. I is a scalar. So when you define the inertia tensor with respect to a principal axis, then it just behaves like a scalar quantity. So moment of inertia in general is a tensor of second rank. But moment of inertia with respect to the principal axis is not a tensor of second rank, it is a tensor of zero rank. And a tensor of zero rank is called a scalar. So I in this equation is a positive scalar. Have you understand? What is I in this equation 3? This is a positive scalar. And if I is a positive scalar, you know, then direction of L will be just the direction of omega. Okay? So in this present situation, we can say that angular momentum vector L is directed in the direction of angular velocity omega. Have you understand clearly? Definitely you have understand. So I have mentioned it here, you can see where I is the scalar, not a tensor of rank 2, it is a tensor of rank 0. Being the moment of inertia about this axis, okay? The angular momentum vector L and the angular velocity vector omega are along the principal axis, and hence each will have 3 components along the axis of any arbitrary coordinate system, let us say x, y, z, okay, fixed in the body, which is actually called the body coordinate system. So in the body coordinate system, if Lx, Ly and Lz are the x, y and z components of the angular momentum vector L, then L is expressed like this. This is Lxi plus Lyj plus Lzk. And similarly, omega is equal to what? Omega is equal to omega xi plus omega yj plus omega zk. But you have seen that this L is equal to I times omega, so I times omega. Here you don't say that I is operated on omega, but you have to say I is multiplied by I. we are taking the multiplication of I and omega, because I is now a scalar. Okay. But if two vectors are equal, you know the corresponding components of two vectors are equal. So definitely the x component Lx of angular momentum vector must be equal to I times omega x. So Lx is equal to I omega x, Ly is equal to I omega y, and Lz is equal to I omega z. Okay. This fact you have studied in your lower classes in +2 level in moment of inertia chapter. Actually in that level, we always talk about the moment of inertia of a body about the principal axis. So the word principal axis is not used there, because it is understood that we always talk about that particular axis. But in present case, we have seen that there may be a coordinate system which is not principal axis coordinate system, and moment of inertia will be not a scalar, not a tensor of zero rank, but a tensor of second rank in Euclidean space. Okay, and so that is called inertia tensor. Its behavior is entirely different. Okay. Now, using the symmetry property of inertia tensor, and using equation A and 4, this equation 4, and you have seen earlier equation A which I have obtained in the first lecture on this angular momentum vector, this equation A. Now you can see Lx is equal to this much, but when we talk about the principal exchange transformation, then Lx is equal to I omega x, okay? And in the previous lecture you have seen that Lx is equal to this much, Ixx omega x plus Ixy omega y plus Ixz omega z. So you can equate both of these. Similarly, you can also equate the values of Ly and Lz. Ly, you have seen earlier that this is Iyx omega x plus Iyy omega y plus Iyz omega z, and presently you can see this is equal to I omega y. Lz, you have seen earlier, this is Izx omega x plus Izy omega y plus Izz omega z, and that in present case it is I omega z. Okay. Now see, if you will bring the terms I omega x, I omega y and I omega z in RHS of these equations in LHS, what will be now your equation? You can see this will become Ixx minus I times omega x plus Ixy omega y plus Ixz omega z equal to 0. And similarly, the second equation now becomes Iyx omega x plus Iyy minus I omega y plus Iyz omega z equal to 0. Okay, you can see. And third equation becomes like this. You can see. In matrix form, you can write down this linear equation in this form. This will be a 3 by 3 matrix. See here, Ixx minus I, Ixy, Ixz, Iyx, Iyy minus I, Iyz, Izx, Izy, Izz minus I. And that will be operated on this column matrix or column vector omega x, omega y, omega z. When you will take the multiplication of these two matrices, you will get these three equations. Now you can see these are the three linear equations. Okay? And you know from the theory of determinant that this column matrix or this column vector will have non-zero value only when the determinant of this 3 by 3 matrix will be equal to 0. So you can say for non-trivial solutions of the equations in 5, we must have the determinant of the coefficients of omega x, omega y, omega z equal to 0. That must vanish. So for getting the non-zero value of this column vector, we can write the determinant of Ixx minus I, Ixy, Ixz, Iyx, Iyy minus I, Iyz, Izx, Izy, Izz minus I is equal to 0. Okay? Now you can see, actually this determinant is cubic in I. Actually, first of all, you can see that this determinant is called actually the secular equation. What is called this? This is called secular equation. And its solution is known as, its solutions are known as secular values or eigenvalues. Okay? This particular determinant is known as secular equation. And solution of these secular equations are called secular values or eigenvalues. And you can see, since I is present in 3 elements of this determinant, so definitely this equation will be cubic in I. I cube term will be present here. And you know, the root there are three roots of a cubic equation. So definitely, since this equation is cubic in I, so there must be three values of I. And if you denote all those three values by the symbol I1, I2, I3, then actually these three values are the three principal moments of inertia of the body. Okay? Because I represent the principal moment of inertia, so this I1, I2, I3, these are the three principal moment of inertia of the body, or these are the three eigenvalues of the body. Okay? Now, after knowing the principal moment of inertia, there is a important question whose answer must know you. How we can find the direction of a principal axis? How we will select a principal axis? Okay? So this is our task, this is our problem. Selection of the direction of principal axis. Actually, if you want to know the direction of any particular principal axis, then you have to choose any one value from this I1, I2 and I3 at the place of I. So I have mentioned, you can see the direction of any principal axis is determined by substituting for I equal to one of the three roots. That is, if you want to find the direction of first principal axis, that is x-axis, then you should take I1 at the place of I. If your aim is to find the direction of second principal axis, you should take I equal to I2. If you want to find the direction of third principal axis, you must take I equal to I3. Okay? So when you will take I equal to, let us say, I1 in equation 5, here our equation is 5, this I and this I will be replaced by I1. Okay? And then we determine the ratio of the components of angular velocity, that is omega x is to omega y is to omega z. That is, if you consider that omega y by omega x is equal to lambda 1 and omega z by omega x is equal to lambda 2. In other words, you can say that omega y is equal to lambda 1 omega x. Okay? And here you can say that omega z is equal to lambda 2 omega x. Okay? Then, now put these values of omega y and omega z in the expression for omega. You know, omega is equal to omega xi plus omega yj plus omega zk. Omega xi is attached, but at the place of omega y, you will write now lambda 1 omega x, and at the place of omega z, now we will write lambda 2 omega x, as you can see it here. Okay? Now you know, as our first principal axis is directed in the direction of Lx, it is directed in the direction of omega x. Okay? So, or you can say that in the direction of it is directed in the, so since it is arbitrary, so you can say that it is directed in the direction of vector L or vector omega. So now you can find a unit vector in the direction of omega which will represent the direction of first principal axis. And how a unit vector in the direction of omega will be found? When you will divide vector omega by its modulus, you will get a unit vector omega hat in the direction of omega, which is the direction of the first principal axis. Okay. So omega hat is given as omega over mod of omega. You can see this is the expression for omega in which I have written in numerator, and modulus of omega will be what? That will be omega x times a square root of 1 plus lambda 1 square plus lambda 2 square. Now this omega x and this omega x will cancel out, and this omega hat is equal to this much. In this way, we can find this omega hat which represents the direction of the first principal axis. Okay. Now in the similar manner, taking I equal to I2 and I equal to I3, you can find the direction of the second and the third principal axis. So I have mentioned it here, you can see. Hence we can determine the direction of omega or direction of principal axis corresponding to I1. Okay. Similarly, if we substitute I2 or I3, we may find, sorry, the page has been turned, but this will be just okay. This is only 1 minute has been left for the completion of video. So you can see, similarly, if we substitute I2 and I3, we may find the direction of the corresponding principal axis using equation 5. Okay. And as magnitude of the angular velocity is arbitrary, you can take any magnitude, you can rotate the rigid body with any angular velocity in magnitude, and we are free to take its any value. Okay. Only you have to select the direction of omega to find the direction of the principal axis. So I hope after these two lectures on angular momentum and inertia tensor, now the concept of the principal axis transformation, the concept of inertia tensor, the concept of angular momentum of a rigid body, all have been clear to you. Okay, thank you very much.